On a blisteringly bright afternoon in 1666, Sir Isaac Newton reclined beneath a sprawling apple tree and watched a single red apple detach from his branch. As it tumbled toward the ground, his mind raced. What guides the apple's swift descent? How does its speed change each instant? In that quiet moment of wonder, Newton glimpsed the hidden power of calculus, the language of change and motion. Now, imagine you're skating down a long driveway. You glance at the speedometer on your phone and see you will average 10 miles per hour over the past minute. But as you swoop around the corner, your speedometer flickers. 12, 15. You feel the change, faster here, slower there. But how would you describe exactly how your speed shifts at one fleeting instant? That question is exactly what Newton chased when he invented his method of fluxions, his secret code for capturing instantaneous motion. Newton pictured motion as a river of moments, each flowing into the next. He thought of your skateboard's distance traveled, call it x, as it changes with time t. If you measure how far you go in a small chunk of time, say from t is equal to 2 seconds to t is 3 seconds, you get an average speed. But if you shrink that time chunk to t equal to times to t equal to 2001 seconds, your average speed inches closer to your true speed, right at t equals 2 seconds. Newton discovered that by letting that time chunk grow ever tinier, approaching zero, you review the skateboard's exact speed at a single instant. He named that magic trick the limit, and the resulting value the derivative. Across Europe, a brilliant young mathematician named Gottfried Wilhelm Leibniz was crafting his own version of calculus. One evening, in 1675, by candlelight in his study in Paris, he inscribed the symbols that are still in use today, which hints at an infinitesimal change, a whisper of movement in y and x. Leibniz's notation turned the calculus into a clear, flexible toolkit. You could slice motion into tiny pieces, examine each sliver, then stitch them back together to understand the whole journey. Picture Newton and Leibniz racing through different landscapes of thought. Newton sprinted through the orchard of physics' gravitational pull, planetary orbits, the motion of cannonballs. Leibniz strode in the garden of pure mathematics, proving his symbols to elegance and breadth. Though they never met, their ideas intertwined like parallel threads in a grand tapestry, each strengthening the other, until the fabric of modern science shone bright. Fast forward to today, calculus powers the rockets that carry satellites into orbit. Engineers use derivatives to ensure a bridge can flex safely under a roaring wind. Doctors rely on integrals, the sibling of derivatives, to calculate precise dosage of medication your body absorbs over time. In computer graphics, artists use calculus to model the smooth curve of a dragon's tail or the shimmering waves of a virtual ocean. Even your favorite video game taps into these ideas to simulate gravity, evil collisions, and the fluid motion of characters leaping through the air. Close your eyes and see yourself standing before a chalkboard. In one hand, you hold a bouncing ball. You drop it, and a classmate with a stopwatch calls out the height every split second. You sketch those heights on the board, connecting them with little segments. Then, you imagine making those segments finer and finer, until they blend into a smooth curve. That curve is the ball's journey. Now, focus on a single point on that curve. Say, 1.2 seconds after release, the slope of the tangent line there tells you exactly how fast the ball is falling at that moment. That slope is the derivative in action. Tomorrow, you might wander into a field of wildflowers and ponder how the petals open at different speeds with the morning sun. Or you might track the temperature change outside and wonder how quickly the world warms up hour by hour. With the spirit of Newton and Leibniz whispering in your ear, you realize every change around you, no matter how small or grand, is a secret waiting to be uncovered by the magic of calculus. So pick up a pencil, draw a curve, and ask yourself, how steep is this hill? right here. How fast is that roller coaster speeding at the top of its loop? Every question you chase will deepen your understanding and lead you straight into the thrilling universe that Newton and Leibniz first dared to map out. Your journey into calculus begins with a curious question. What if we could speak the language of change?